So, hello everyone. Welcome to the final session for the day. The final session is a tutorial session, and this will be given by Professor Rabeet Singh. Professor Rabeet Singh obtained his PhD from IIT Kanpur, and after postdocs at NICER Bhubaneswar and ISC Bangalore, he joined BHU as an assistant professor. His research interests are electronic structure theory, computational material science, and machine learning. And he will give the tutorial session for the day, so make sure to clear all your doubts. Professor Singh.
Thank you so much. Thank you. So, okay, from the morning we have learned a lot of concepts, and we knew about, we got to know about the functions. So, how many of you are aware of the functions? Let's go to the how many of you are not aware of the functions? But many of you are not aware of the functions, right? So the way I'm going to proceed is because I'm not going to tell you something like without knowing that you got to know about it or not, whether you understood it or not. So let's first talk about the functionals. We know about the functions, right? In case of functions, we have a input variable, and for each input variable, we have a mapping for the output variable, right? For each independent variable, we have a dependent, right? So it's like a point-to-point mapping. For 1 point, you have a 1 output, right? For 1 point of input, you get 1 output, right? So the difference between function and functional is that in case of functional, your input will be a function, not a variable. So let me give you many examples. Like if you all know about in quantum mechanics, expectation value, right? Calculate. So these expectation values are the functionals of a function. All right. That means you will give us a wave function, and what will be outcome? Output will be a number, right? For each wave function, we will get a number. So in case of functions, your input is a function and output is a number. All right. So in the morning we had to put in a functional like we have a functional rho. That's a sign of function. That is, if we put a square bracket, it means it's not a function, it's a functional. And it's a functional of density. Whenever we have an input density, we will get a number. Right? And also in quantum mechanics, we know energy function, E psi. E psi is written as psi star H psi and the integration over volume L. It is the energy function of the wave function. Right? Now, we all know about that whenever we need to solve a problem in quantum mechanics, we have to solve sorting the equation, right? Sorting the equation. And once we solve sorting the equation, what we get? We get the wave function. And from that wave function, what we do? We can calculate the various quantity as an expectation values, right? Can I make sure that everybody understands these expectation values? Whenever we say, okay, we are talking about expectation value. Everybody understand? Okay. So and how do we do that? So the problem in quantum mechanics is something like that. For a given potential, we calculate a wave function psi rt And to get this IRT, first we have to calculate psi n. So psi n is the solution of time integrated solution. Yes. So whatever potential we will consider, each potential will be time independent potential. All right. And once we know this psi n, we calculate our psi r comma t, something like this, as an expansion with Cn psi n x e to the power minus int upon h1. Right? That's how we solve the problem in quantum mechanics. Once we know psi RT, that means then we know the dynamics of this system. Right? Now, solving the Schrodinger equation is equivalent to minimizing this energy function. How can we see that? We can say that because whenever we minimize it, E psi, let's say with respect to psi, with the condition that psi is an unrealized function, the condition for the whenever we say we are minimizing E psi means we will take a functional derivative of E psi using something called Lagrange multiplier. So this E I take out because it's not the same E. So we take a Lagrange multiplier and then psi. So whenever we do that, take this functional derivative, we will get something like integration delta psi star h psi minus E psi BR and plus its complex conjugate information. Right? So if we are given a complex number, let's say, right? And add a add a complex conjugate of this number, then what we conclude? We conclude that whatever complex number we are considering should be equal to 0. Right? So it means this integration can be written equal to 0, and it should be true for all the delta psi star, which means h psi should be equal to E psi. Okay? H psi equal to E psi, which is a Schrodinger equation. E actually is a Lagrange multiplier. I'm putting this E because if you want it to write it something else. Maybe expectation value of that. Because it comes out to be equal to capital E, total energy. That is why I am taking this. Or let me write this. I'll take this as a expectation value of capital. Yeah. Maybe and I take E. I think I understood. So
time independent solution.
Yeah.
One is IEHT, that's the same as that. The e power minus IE by h that you have written. It's the same E as that, right?
Here energy is the energy ion direction. Sorry, so it means so just give me 10 minutes, then I will start. It means whenever we are solving Schrodinger equation, we are finding a psi which minimize the energy function. And what is this H psi minus E psi? H psi minus E psi is the functional derivative. Expectation value Hamiltonian with respect to the condition that psi is a normalized quantity. So we can also write it equal to H psi minus E psi. Functional derivative. Now we know that if we are given a function, let's say a function fx, and if we have a local minima, let's say that minima is here, and if you want to go towards this minima, what we do? So we already know that at the minimum, at prime x equal to 0, right? So it's a single point, right? Whenever we minimize a function. Let's say if we have a two-dimensional function, x and y, then we will have a two condition, at prime x and at prime y, at prime with respect to y, with respect to x should be equal to 0. If we have a three-dimensional function, we will have a three such equations, right? So if you want to move towards this minima, we can construct a very simple procedure, something like this: xn plus 1 should be equal to xn minus alpha at prime. Right? Something called gradient descent. For this, we can simply understand that whenever we are here, we should come back. Right? Here, your f prime x is positive, means we will come back towards the minimum. Here, your f prime x is negative, which will go towards the minimum. Right? In the same way, you can construct a procedure or a scheme, something like this, to calculate the wave function using the functional group. Okay. As it is, has somebody solved Schrodinger equation using functional derivative? No. So I tell you one of the way. What you do is, because if you use directly here, it means this psi will be given on a grid. Let's say if you have 500 points, then it will be given only 500 points. Then this problem is very unstable because you don't know whether your psi will be a well-behaved function or not, right? Because it's going from 0 to infinity, up to the infinity. So what we do is we can reduce our space. How do we reduce? Maybe we can explain the psi in terms of some basis. Right? So whenever we say we are expanding our psi with respect to some basis set, it means then we will look at the derivative only with respect to Cn and minimize the energy with respect to Cn. So it's like in variational method, if we have a two parameters, we get two equations, right? If we have a wave function, let's say having parameters A and B, what we do, we take derivative with respect to A, derivative with respect to B, and then we calculate A and B, right? So in the same way, if we expand this wave function in terms of some basis set, then we have to minimize our energy with respect to Cn. So whatever functional derivative is coming here, it will transform into the simple derivatives. Whatever functional derivative is coming here, it will convert into the simple derivatives with respect to parameters. All right. So this is one other way of solving the equation. But usually, what we do is we simply solve Schrodinger equation on a grid, and for that, what we need to remember is uh, so let me give one of the example. So let's say one of the very simple examples we have let's say we have an infinite potential, and inside it we have a zero potential. But and your Schrodinger equation looks something like this: p2 psi over e square equal to e psi. Right? For this problem, we already know the solutions, right? Analytical solution. Has anybody solved the infinite world problem numerically? Numerically, you did it. We solved it numerically. Huh? Eating numerical. Is it done? No. So of course, so what we do is whenever we want to solve Schrodinger equation, what we need is let's say initially we know the wave function, and that value is psi g. So we are working on a grid, and this is our 0. This is our next point, let's say 0.1, and we have the next point 0.2, and then we have next point 0.3 or delta. If we are given a wave function at x equal to 0, and if we need the value of this function at x equal to 0.1, what information do we need? Radial, right? So we need the derivative of psi, which is psi prime x. So let's say this is our step size, which is 0.1. Then we can calculate psi 1 something like this. Psi 1 equal to psi 0 multiplied by h psi prime x. Right? What is the problem in this method? We are taking linear approximation. So which shouldn't be the case, you know? Real. So we need some better approximation, but right now I'm not going to go there. First, we will see if we can how we will approach. We know if we know that we can go to psi 1 if for a given value of psi 0 and psi prime x. So if we want to calculate psi 2, we will use psi 1 and then multiply it by psi 1 prime. Do we know psi prime? Psi prime x. We know it. Huh? We need we need a psi prime max at all the points. Not only on the single. Even at the initial point, do we know it? So, so what we will do is, so initially, actually, for some problems, maybe you might guess it, right? But for this problem, let's say for infinite problem, we may choose a small value of this derivative, 0.01 something. It might be wrong. It might be wrong. But we have to start our iteration. We have to start calculating something, right? Because we have no choice. So maybe our initial guess is wrong. But what we know is, we know that if we are given a psi prime at x equal to 0, we can calculate psi prime 1, that is at x equal to 0.1. ठीक है psi prime को ऐसे ही निकाल सकते हैं What is psi double prime x? Psi double prime x? Sure. 2 is So psi double prime x is equal to yeah, it's fine. Okay. Now it might be the wrong psi prime x initially, but because psi double prime is calculated exactly within certain equation, so maybe after 1 or 2 steps, it will come, towards the exact value of psi prime. If after 2 or 3 steps, maybe a little bit error will be there, but you will get the correct size. What about energy? Because if you want to calculate psi double prime max, you need energy also. Numerically, you don't know what is the energy. What is psi double prime? Hey, what is the energy? You know what is the energy, right? This is the energy eigenvalue of this particular equation. But numerically, we don't know what is the energy. And what should we do? Huh? Nobody has the answer. This is surprising. We don't know energy actually. So for that also we will guess some value. We'll guess some value. And in case of infinite well, what we know the boundary conditions. Maybe we don't know energy, but we know the boundary conditions. What if it is not the correct energy? Whatever energy you have guessed, whether your wave function will satisfy boundary condition or not?
Impose such that
We will
impose the conditions such that we can also consider both by the
be boundary. So we will get some energy capital E, and once we have guessed in capital E, we will calculate psi double prime, and we will use this psi double prime to calculate psi prime, And from psi prime, we will construct our wave function. Now let's say we have infinite well, and initially we made something like this. If energy is not the energy eigenvalue of particular equation, you may end up something like this. It means because your actual wave function should satisfy the boundary condition, which is it should be equal to 0, right? So if you start from x equal to 0 and x equal to a, your wave function should be equal to 0. Okay. So we have got one of the idea. What we will do? We will initially choose. We will initially base some value of energy, and using that energy, we will calculate our second derivative. And using that second derivative, we will calculate first derivative, and from first derivative, we can construct our wave. If this wave function is not equal to 0, at x equal to a, at the boundary, then we have to change our energy. So simple way is maybe if you know you have some idea, maybe energy for in case of infinite well, maybe it is going from some value 1 to 10, something like that. Right? You can choose that range and keep on changing energy. So for each energy, you have to make sure that your wave function is whether your wave function is satisfying boundary condition or not. If it is not satisfying, then that energy will not take, change it, again change. Something like
When the wave function is not zero, is that non-zero value can be make the guess for the E
if wave function is
not zero, then
Will
that
come.
error can be
it will come. So right now, because for that we have to go further. But right now, because I want to make sure whether this simple thing is basically can be understood by everyone or not. So now I'll put another situation. Let's say with for some energy we have come here. It's a 0, right? Now our wave function is satisfying the boundary condition. Is it the sufficient condition for the solution? Why?
because in there may be many wave functions with the same boundary condition, but still not be an eigenstate. It's not the need not to the
That's okay. If you give any, that's okay.
but that is but that see you have energy, you get a wave function. I mean that's why it's not still in that case there might the wave function may not be an eigenstate because it's not a lesser condition.
Why? Why?
Because you can construct any function, right? I can just draw like that.
What now? No. Just remember, you cannot construct anything. We are coming from the second derivative. We are coming for the second. First derivative continue. What was in case of infinite well, whether first derivative is continue? Huh? Which our point. Okay. So see, why we cannot take this solution? Because there might be many solutions, something like this. With this derivative, or with this derivative, or with this derivative, you can have a many solutions. Right? And what will happen whenever you will make a program, energy will change a little bit. Like maybe at the fourth place of decimal place, something like that. So we get multiple values. So now there is another problem. But we don't know which one we should take. Because derivative we don't know. What should we do? I'm getting it right because we have talked about managing things properly, and we cannot solve even a simple infinite problems very well, right? And how could you do it? DSP, or how will you make your program, or how will you make sure whether it is working fine or not? So, किसी को कोई idea? Do you know the data? Do you know the data? Huh? No.
So can we make it? Can we make it periodic and fix it?
No, no. I'll tell you what we will do then. We cannot take this point. What we will do, we will choose another point where we can satisfy our ends. So I'll tell you which way we can do that. We will not go this way. We will go this way and will come from this backward. You will come from infinity, from infinity in the backward direction, and from 0 to forward direction. So the point where we can check, we can put our boundary condition in this one. Right? So what should be the condition at the middle point?
The derivatives.
Derivatives should also. यहाँ पे वो वाला प्रॉब्लम नहीं आएगा, right? Right? Huh? It matters that your derivative will be different, but both sides it should be same, right?
Order is
Hmm?
order is same, but signed by every. So where apple
More value,
derivative. Like we're taking derivative.
it will come something like this. It's the same. Either it will go like this, then it's 0. Either it will go like this, and I'll make it. So in case of ground state, it should be equal to 0 on side, right? In case of, let's say, first excited state, you will have something like this. But it should be same derivative, right? So the best way is we will build our solution from both sides and put the boundary condition at the middle. Yeah, Abdul sir, now I'll do another question. Can we take the middle point for each system to satisfy our boundary condition? उससे भी पहले there is another question. Now let's say if you want to calculate ground state, because this way you can have any state. We don't know which one we will get, but specifically we want to calculate ground state. Then what should we use then? Well, which information we can use to calculate ground state? Thanks. Maybe some minimum
Numbers
number of nodes. So nodes, by counting nodes, you can make sure which state you will have. In case of ground state, you will have 0. In case of excited state, you will have 1 node, right? And node you can count with your program. So how will you count node?
zero values, taking where size zero.
Well, like
So checking quest I see. That's how it's zero.
Is 0 or?
Shy is zero or not? Okay.
No. 0, you know how difficult it is to satisfy this condition that wave function should be equal to 0.
We can change the points.
Have you tried? It's a very, very difficult because coming equal to 0 wave function, you have some grid, right? 0.1 or 0.001. It's very difficult to satisfy.
Changing signs or not? Why values are changing signs?
Sign. So its wave function changes sign, I think. From positive to it will become negative. From negative to. So you count how many times your wave function is changing signs. Because you are making it. Okay? So, okay.
Actually, yeah, good job.
Thank you, sir. So, now next thing, would be some unit test. And what I want basically my plan is this. I'll tell you everything about this. Which way you can basically satisfy boundary condition and how, whatever information is required, I'll tell you everything. You may be able to phone call. It's a very simple, right? You can try. If you are not able to do that, just let me know. I'll do. Okay?
So, this is very certain algorithm, right? Very certain algorithm, right?
This sorting algorithm we are not using here. Right?
Not exactly like you.
But for sorting algorithm, we want to check whether energy is higher or lower. Here. Okay, whenever we are counting, then we need to do it. So, okay. So this is a very simple case. Now we know that maybe because energy eigenvalue have some gap, right? Maybe here, then here, and here, here. So this is the ground state, then you have excited state, and you have. So there is a difference, right, between two eigenvalues, right? So if we have energy, or if we let's say if we have one node in the wave function, it means our energy should be equal, right? But it doesn't mean you will get exactly equal to E2. Maybe it's a little bit above 2E2 or a little bit below 2E2, right? So it's all right. You can, while counting the node, you can make sure, okay, I am close to first excited state. But what I want to come back to the ground state if you want to calculate ground state. So then how will you basically come back? You don't know, right? So maybe I'll tell you what one. So you counted one node, you were close to the first excited state, then you change the energy, you can somewhere in here, close to ground state. Huh? Now what will you do then? How will you make sure whether we should increase energy or decrease? That was your question, I think. Right?
I think what online then.
We have 0, no? So your program should be something like this, that whenever you have a little bit, above the ground state, your program should know whether we should increase energy or we should. So I'll tell you how to we do that, but I don't know. Let me accept because I have read that from the book by Paolo Giolici, developer of quantum espresso. So I only know this what is the condition, but I didn't try that derivation. So I'll just let you know. You all. If somebody is able to tell me, so how do we do that? That is determine something like this. Okay, but I'm not sure that will be true for this also. So idea was that if your derivative here, let's say in this side, right hand side, you have a derivative psi prime r. On the left hand side, you have derivative psi l prime. If your psi r prime is greater than psi l prime, it means your energy is greater than E. Derivative, using these derivatives, we can determine. But but that condition is true whenever we have some actual system, let's say hydrogen atom. So in case of hydrogen atom, we match the matching point will be the classical turning point, not the middle point. So at the classical turning point, this condition is satisfied. So okay, now we have all the information. We know we can start from some small value of psi prime 0.01. We can have some psi 0. We already know about the individual, so we can take it equal to 0. And from there, we can construct psi 1 using psi 0 prime x, and psi 0 prime x we will update the second derivative, right? By guessing some energy E. And by counting the node, we will make sure whether we are going to the excited state or to the ground state, whatever state you want to have, right? There you can approach using by counting number of nodes. So okay, so this is the enough information. Is there anything you would like to know? Now we have sufficient information. Can you make a code?
Write a code, but the accuracy level.
It doesn't matter. If you make your first code, then definitely it means now you know enough, right? So then you can improve it. Initially, at least you can make a code. It gives some energy, I guess. Maybe it's accurate up to the third decimal, right? But you should make it. Because even if you make a code for infinite world, and then if I provide you solver for radial equation, you will be able to understand it. Can you make it? I'll help you. Doesn't matter how much time it is taking. I'll individually help you. Okay?
So let's put some price.
Huh?
Let's put some price. Who does it? They get some.
Yes.
Tomorrow again you have a class, right? Day after tomorrow.
So in the first time when you are transferring one end, checking if the base cannot that's kind of boundary condition and the other end. Now let me done it constructing from both sides. How are you going to check if the yes?
So for that, your gain function and variability should match everything.
Okay, so when you are saying they are somewhere around which means you go, is that the whole all of those things is very why is it so hard to get at it?
It's not hard.
Just go on increasing. And at the point you satisfy and then you further
Yeah, so basically you can calculate it. Only thing you can do is you can go up to some decimal cases. But you will put some condition, whether it was psi r prime, psi l prime, a difference between psi l r prime minus psi l prime is greater than let's say it for -6, then you will get.
yeah. So that precision we could go on.
Yes. Okay, so if you want, sir, we can give a price.
Yeah, sure.
Well, I have I have already uploaded lot of code. But if we cannot understand it, then it's not a good idea. I'll never do that. You provide code and you just run it, give some iron and L, get some hiding values. So I like to do like that.
Let's see who does the efficient in this code. And we'll make it a first prize. One prize will be there. Let's see how many.
So can you formulate the question properly? So we just have to wait for that.
Let's try.
We need to make a code.
Yeah.
Which, for which you will give the which energy isotope you want to calculate. Let's say for your code, if you give n equal to 1, it will give you a graph. If you give n equal to 2, it will give a strict set. And only energy eigenvalue you will isolate to it.
So this, different.
Because this is the simplest problem we can think, right? We all know that in quantum mechanics we are taught the infinite world problem. Why? Because it is the simplest problem we can see. And not only that, it gives a lot of insight because this problem has something unique, like it has a derivative discoverability at the boundary. So the infinite. And we will get the idea about eigenvalues and eigenfunctions. And it's the simplest because b equal to 0 inside. And that is why we are taught this infinite world problem. Otherwise, in real life, we will never find infinite world. ठीक है सब बताइए हैं सब
So make it in a
and don't worry, I'll till tomorrow, till the next session, at least I'll bring you at a point where you can solve a hydrogen like system. You can solve a radial equation. You can use a local density approximation, or you can use any function. So I provide you that code. But before that, I want to make sure at least you are able to understand.
If there are many people, give 4, 5.
Huh?
Give something. What? We'll do for all the tutorials. See that it's the maximum. See, this is good, right? So, here should we implement symmetry? Why were you doing it symmetry? So for the middle point, in the boxes. So I R prime for I N prime just come for I R prime for
It should be equal to, but this is not whether it will increase in or decrease in. You can definitely make the difference is greater than something and it keep on increasing. That way you would know that which you should whether it will increase or decrease. Or you can simply manually you can just give some step size and keep on changing. Whenever it is satisfying, rest come on.
for the class 2 for the class data estate. We have equivalent with functions control ID. So then I get prime and in this relation I have prime greater than I will be first prime.
Maybe this condition I am telling again because this is true for this classical condition. So I have no idea whether so this is one of the but I wanted to tell you but I don't know whether I didn't check. If you are making a code, you can check whether it works for this word or
Sir, when we are posing this condition that shy left is equal to shy right, so are we not thinking that
It's not proper. It is not linearity because it's a individual, it's a symmetric potential. So of course we have it's a symmetric potential. So as it material, as the material, you will be anti-symmetric. The condition is simply for symmetric potential, you will either have a symmetric solution or the problem in between. Okay, so I'm erasing it. I'll come to another topic. So the actual problem we will have with the radial equation. So radial equation we get for spherically symmetric potential. So our potential is not spherically symmetric. We cannot separate the radial and the angular part. So I'll tell you whenever even if we are using aggregate. So in case of aggregate, if we are using let's say for helium atom, so helium atom will have this 1s orbital. In that orbital, it will have both. So it's a spherically symmetric orbit. So for that case also, you will have a spherically symmetric potential whenever you are using aggregate. Similarly, if you have a density which is spherically symmetric, which is the case for this closed cell atoms. So in that case, we have this spherically symmetric potential. So if you know how to solve the radial equation, then definitely you can solve a lot of problems. It's the atomic problem. Okay. So what is the but before that, so we have our SI equal to ESI, which is the case for time independent potential. And our Hamiltonian in general is equal to sum over I carrying square upon plus sum over I carrying square upon 2 plus sum over some B external potential sum over I and plus electron interaction on Ri of J and plus nuclear interaction could be I J 1 over Ri minus R. Right? This is how we write our general Hamiltonian. So for each electronic system, you will have a nuclei and you will have electrons. You will have a nuclei interaction. You will have electron nuclear interaction. You will have electron nuclear. Right? That's about nuclear. Now, many of us have read about the Born-Oppenheimer approximation. Right? What is the basis for that approximation? Electrons are moving faster than nucleus. Mass of nucleus is big. So electrons are very, very heavy in comparison with electrons. Nuclei are very heavy in comparison with electrons. This is the basis for born Oppenheimer approximation, right? So इसका मतलब ये होगा. It means we can ignore this term, right? Right? Huh? This one. Only this one we can ignore in comparison with this one. It is the only condition we have to make sure. Let's assume P. So PI is also there, capital PI, right? Maybe your PI is also very large, right? So just let me know how will you decide? Because if you use this approximation only that your mass is very large in comparison with electrons, right? Then that's not the enough information. Maybe your this momentum is very high. So how do you make sure that this momentum, capital PI, is comparable with small p? But without that information, you cannot use simply saying, okay, PI are very heavy and let's remove that. Can we say anything about capital PI? Is there any comparison of capital PI with small PI? So of course the momentum conservation rule will still be there. The electrons are like moving, let's say something is going in the right hand direction, so similar momentums will be in the left hand direction. And your nuclei are very actually this would be safe, right? So it means capital PI are comparable with the small p. Now we can use this approximation when nuclei are very heavy. Let's remove. Right? So let's remove this. Okay. If we don't remove this term, what would be our solution? Psi. Psi should have capital Ri, right? Set of capital Ri and small ri. This is the whole set, okay? I mean R1, R2, R3, Rn, and small r1, R2, R3, Rh, right? So that's the wave function we will get. If we don't remove that term, that will be it, right? So, and that wave function will have some kind of structure. Because whenever we are solving the equation, we get a form of wave function, right? Which has some structure, right? So if we remove that term, then what is the difference? Because so let me tell you. So initially we have this term, we got this one. Next time, let's remove this term, and then we got another solution. Psi. Will it have a capital R or not?
There is no variable of R. It's R value.
So it should have a capital R or not?
Not R, it's constant value, like a constant R, constant capital. Because the external is also
Constant. So he is right. Because whenever we remove that part, your nuclei are now fixed in this space. Alright? So it's like that for a given configuration of nuclei, we solve Schrodinger equation. And the position of nuclei will come as a parameter to the solution. Right? So the only difference is now that in this case, your Ri is also changing, but in this case, this Ri becomes a matrix. Okay. Now, let's say we for the given configuration we have solved our Schrodinger equation. For the given configuration of nuclei, we have solved also Schrodinger equation. Now, if we change that configuration, what do you think? Can we make sure that your wave function will still remain in the ground state? Are you getting what I'm asking? Now, if we change the configuration, because what I frame the way because maybe you all know about it.
Adiabatic or
Adiabatic approximation. So here comes the adiabatic approximation. And it is possible because nuclei are moving very slowly, right? And because they are moving very slowly, then your ground state should remain actually it shouldn't change, right? Because they are moving very slowly. And I hope everybody knows about adiabatic approximation, right? Slowly, I think that, there is a chapter about the two kind of approximations are there: sudden approximation and the adiabatic. In case of sudden approximation, your solution changes. So the older solution is written as in terms of the new basis, which is obtained in the new potential. And in case of adiabatic approximation, your solution remains same, just change that parameter. All right. Okay. Now, because it's a huge system, right? Because we see it, right? So we can never, you will find it impossible to solve the general problem using variables. I'll tell you, I'll give you one of the roughly estimate. So estimation is something like this. Let's consider helium. So in case of helium atom, your Hamiltonian will be 1 by 2 L1 square, 1 by 2 L2 square, minus 2 over R1, minus 2 plus 1 over R1. That is R1 minus. And your Schrodinger equation will be at psi equal to oh. So let's roughly estimate. Let's say there is no symmetry, right? We know how to solve a one-dimensional problem, right? On the grid. So let's say there is no symmetry. And how many variables will be there? 6, right? X by x1, y1, z1, x2, y2, z2, right? So if there is no symmetry, and let's solve it directly. Directly means in the same way on the grid. If you just add x plus, if you know the solution at x, you calculate x plus x, psi x plus x, right? In the same way. So whenever we are solving that way, it means at least we will store that way function, right? Somewhere. Because we are making our code changing, so we will store it, right? So let's try that. So let's say in one direction you have taken 500 points, or simply let's say 100 points in one direction. If we have a 6-dimensional space, dot 10 to power 6. 10 to power 6 means 10 to power 12 points will be there for each energy. For each energy eigenvalue, to store this wave function, you will need 10 to power 12 bits, right? So what kind of point these will be? Floating numbers, right? Wave function store kar rahe na. So floating numbers should be there, right? For one floating number, how much memory do you need? Hmm? Simply, it depends on what is the precision, real time and double precision. So in case of real number, you will need 32 bit, right? 32 bit. For each number, you will need 32 bit memory. So it means 10 to power 12 point will need 32 multiplied by 10 to power 12 bit. Can you convert it into the GB? Because we are familiar with gigabyte. Can you convert it into the GB? Huh? 4 terabyte. Now assume. And this much energy will be needed, even storing this wave function single time. And this is the simplest problem you can see. This is a helium. If you have a 3 electron system, 4 electron system, then you can imagine, how much energy you will need. Now I will tell you one of the, because this is something made me curious. So I thought I'll test. I check it whether I can store that wave function or not. But I didn't know how, because initially I didn't calculate it. So what was there? I had to give a talk in my department. So because I had to give this idea, so I have run that calculation to store the wave function. And so I did it, like in the evening. That program, uh, 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 then I came back in the morning. It was still running, okay. And then whatever talk I was making, I just put that run option in LaTeX. So whatever LaTeX file was there, it was I lost that file, and there was a zero memory in my computer. So now you can imagine how difficult is this to solve a many response problem using waveforms. Okay, but we do that, right? Today we are able to solve even 100 electron system, and it is possible because of the density functional theory. And even using wave function, we solve a 20 electron system. It is possible because lot of approximations are taken, lot of symmetry are available, right? And that is why it is possible. So okay, one more question I will ask, because I know that is how I teach my students. I know that you will not ask me, then I will ask you. So another question is, this is our Hamiltonian, this is Schrodinger equation, right? In the right hand side, we have energy capital E, which is a finite number, right? It is finite always. In case of infinite value, it's finite, right? Or in case of hydrogen atom also, we have a finite energy, right? We also have a wave function finite everywhere, because if it is not finite, then we cannot normalize it, right? So only wave function we take in quantum mechanics are denormalized wave function, right? Right? So in the right hand side, we have a finite number, and in the left hand side, we have like psi, and psi is finite everywhere. Now, think it at r equal to 0. Whenever r1 is going to 0 or r2 is going to 0, what will happen? Whenever r1 goes to 0, Your potential is 2 by R, right? Right? In the right hand side, we have a finite number S I. Oh, E side. In the left hand side, your Hamiltonian becomes infinite, right? At R1 equal to 0, at R2 equal to 0, and at R1 equal to R2, vector R1 equal to R. There also. एक problem हो जाएगा whenever you are making a code, you face this problem. Infinity. So how will you take care of? Huh?
The function is 0.
Wave function, right? Wave function. Okay, I'll tell you. At R equal to 0, what is the ground distance of hydrogen? It's a finite, right? So how can you say it's zero? बताओ क्या करोगे? How will you tackle this problem? Okay, that's one of the options. Okay, let's not make it equal to 0, right? But actually it will become 0. Huh? Then for other people, none of you have this kind of problem. It's very surprising. No, you don't need that. This is no. नहीं किसी के पास आंसर नहीं.
We can do power series expansion of 1 by R. That can be done.
Power series expansion.
Yeah, like monopole, dipole, we can expand 1 by
How
R.
would you remove this 2 over R? Even let's say, how would you take this power series expansion? Because R1 equal to 0 should out, because it should be satisfied, right? Whenever you are making the power series.
Yes, yes.
So I'll tell you how is it taken. There must be some term in the Hamiltonian. There must be some term in the Hamiltonian which will cancel this 2 over R1 term whenever R1 goes to 0. So that's how does it happen? You know, using this condition, you can calculate ground state of hydrogen atom even without solving the equation. You will just need to solve the first order differential, not the second. So tell me, where will be that term? With the same behavior, 2 over 1 over R. This is the 1 over R behavior. Where is the other term in the Hamiltonian which has the same behavior, 1 over R? Yeah, but in the kinetic energy term, we will have that behavior. No, you are thinking, right now we are looking at. So I'll tell you where that term is, because we know the radial part of this Laplacian equal to d2 over dr square plus 2 over r d dr and plus angular part, right? Now you can see that 2 over r has this same derivative. So somehow this will cancel that term. So how will you do that? That's your wave function, So let's include that term 1 by 2 multiplied by 2 over r. This I think 1 over r will be. So your wave function, whatever wave function is there, dr over dr minus 2 over r multiplied by r should be equal to.
So sign actually sign should be negative. Oh, yeah.
Psi.
Sign.
Oh, no, it's all right.
It's all right. By r d by dr.
Because minus sign is already out.
And then how we can cancel these two terms? Because
We will make it, then it means we should have a negative dr over here, right? So let's remove it. 1 over r will go away, 2 will go away. We will have 1 by 2 d capital R over dr minus r equal to 0. Right? It means your r should be something like this, e to the power minus 2. You know this solution, right? For hydrogen-like system, if your atomic number is 2, you will get this. So remember, whatever solution you will get from the Schrodinger equation, all those solutions should satisfy this condition. Otherwise, you cannot remove this singularity at r equal to 0. Otherwise, you cannot remove this thing. And this is also required whenever you are making a program. So okay. Okay. Is there any question?
R1 equals to R2.
R1 equal to R2. For that also, I to possibly I have that. But we can, I'll tell you right now. This del 1 square and del 2 square can be written in terms of R1, R2, and R1. Whenever we will write that way, we will get that term 1 over R1. Then we will satisfy that. So if this equal Hamiltonian can be transformed in R1, R2, and R. So I saw that because I have written somewhere else. And it will be available in one of my papers. With a semi-analytical wave function for 2 wave functions. So in that paper, you will get it. So, okay, so I'll stop here, and probably next time I'll give you all the codes. Codes are already available. If you want, you can use that. But before that, I would like you all to try it, make one code, and then use the okay. If there is any question, let me. And I'm sorry, my ES is a little bit more. It's an exact solution that It will be yes. पढ़ाई कौन आता है ना
So thank you, Professor Rabeet Singh, for the tutorial. So this brings us to the end of the workshop for today, and we meet again tomorrow at 9:30. So for all the outstation participants, the dinner is from 7:30 at Vasundhara, the same place where you had lunch. Thank you.
Excuse me, are we going to get a separate Google Meet link for tomorrow also?